Okay. Let's talk about the concept of flux and how we can use it to generate electricity. Flux. Well, flux just means change, right? When something's fluxing, it's changing. What we really want to talk about is magnetic flux. And basically the interaction between a fluxing magnetic field, or a changing magnetic field, and charge carriers in conductors. And the response, we'll say, response of charge carriers. Now, we've sort of touched on this a little bit. Let's put a few things in place first. Okay, so let's imagine that we have a magnetic field. We'll make it towards us for now, for a change. So this magnetic field is facing towards us out of the page, okay? And what we're going to do is we're going to bring a metal ring into the field. Okay, so there's a metal ring, and we're going to push it into the field. All right, so something that I just want to make sure we understand here is, let's say that instead of a circular loop, we have a square wire here. Okay, we have a square wire. Use your right-hand rule to decide on the left and the right which way current will be tending to flow, okay, as we move through here. Well, we think of this as being full of positive charge carriers that can move. It's a conductor. It's got movable charge carriers. Using your right-hand rule, you're going to point your fingers out of the page towards your face, and your thumb is going to aim to the right, and therefore your palm will point down. These positive charge carriers on the left and these positive charge carriers on the right tend to try to become a current, but that opposes itself, right? They're going to maybe come into here and they're going to like smash up against each other. Therefore, there can be no continuous current looping around here. And of course, the ones on the top and the bottom, they'll both have a downward force, which will not contribute to making a current flow in here. All right? So just moving a loop of wire around inside a field does not accomplish the creation of a current. All right? Let's get rid of all this stuff here. Now, what does happen though is as this loop of wire is entering, it is undergoing a magnetic flux, right? It's going from a magnetic field inside of it equal to 0, to at a later time being inside the field, and then having a magnetic field through it, and then if I continue, having that flux drop off. While flux is happening, there will be current. While there is flux happening, there will be current. Inside the field, no. Outside the field, no. But during the transition from 0 flux to having a magnetic field through here, I think they actually just call it flux overall, which I might start doing because it's easier. Maybe I shouldn't though, because flux means change. But we say that inside here, we have magnetic field over the area inside the loop. So before we actually do like calculations, I just want to make sure we understand what will happen. So Lenz's law always says, and we said this in the last one, Lenz's law said that current will be induced such that the induced magnetic field counters the flux change. Okay, that's confusing, but we'll do an example and it should make better sense. So the way we look at this, and the way this is talked about in physics, I'm not sure why it's talked about in this way, but as we're going through here, we get what is called a flux change, which is weird because to me that's like saying change, but that's just the way it's said. Okay, so you go from zero flux or zero magnetic field inside the wire to a flux equal to that magnetic field crossing the area. So you're increasing a magnetic field that's pointing out of the page. So Lenz's law says that while you're transitioning, just during that transition, you will counteract that change by setting up right in here the opposite magnetic field. So if you're building it out of the page, this will coil current such that inside of it, you get a magnetic field that opposes that. So how do you go about doing that? Well, this is now into the page, okay? So we use our cheater right-hand rule to say north is away from us, so the current as I'm entering the field must be flowing around this way. Okay, so think about that. You'd have to come to the side. You'd have to grab that coil with your hand to point your thumb away from you, right? Because the magnetic field's pointing away. And the current, therefore, must be going in a clockwise manner. Okay? Now, once you actually enter the field, you get back to a null situation, and you get no I. So I equals 0, no current here. During the flux change, where you're going from no magnetic field to magnetic field, there is some current, check. Or I guess, hey, maybe a better way if we want to be more mathematical, so we can say it is greater than 0. Now it's 0 again, and now we're leaving the field. So we're going to have fluxing again as we leave the field. Okay, as we leave the field, we will have fluxing again. And since I'm going from an out-of-the-page field to a 0 field, I want to counteract that. So this will now, this will now set up, oh, for goodness sake, this will now set up a field to oppose the loss of field, okay, like so. And now that field's pointing out towards you, use your right-hand rule, put your thumb out, right, because north is now towards you, and you realize your fingers are going to point that the current is now going to run around this way, or opposite to what we were doing before. So this is now representing the current. And so now we have I again greater than 0, but flowing in the opposite direction. And then once we're out, we have, again, no current when there's no field. Okay? So when the magnetic field is cutting through our square, our circle, okay, and we're going from an area of no magnetic field to an area of magnetic field, the current will flow such that we set up a magnetic field inside our ring here that opposes the change. Yeah, I know. Okay, so essentially here's the idea, right? We go from no flux to flux. Okay, so that's a change. And then you have flux through here, which is just, I'll tell you what that is in a minute. And then you go to a flux change again to no flux. So flux is this concept. If I have a coil of wire and I have a magnetic field inside of it, I say this term flux, which has this symbol right here, is equal to Teslas per square meter. How many Teslas divided by the square meters of this thing? Sorry, just fix that. It's not per, it's times. It's Tesla meters squared. Okay, so another way to say that then is just this. It's equal to B times A. So magnetic field strength in Teslas times the cross-sectional area inside the loop. All right. A is area in meters squared. So we know if this is the definition of flux, and its unit of measurement is called the Weber. Okay, so Webers. If instead of pushing, our ring into the field, what if instead of that, we just take our ring and we spin it in the field? We're doing the same thing, right? We're going from full flux when this thing is straight on to, if we say put it on have some way of spinning it, and now we spin it around, at some time later, it's going to be edge onto the field, right? So it's going to have no flux. So we're going from flux, we're going a quarter turn, right, to no flux. So we're spinning around this way. Then we come back around again to being able to have this thing full on, right, to being no flux again. So every quarter turn, you go from flux to no flux. So what's going to happen? Well, just before we wrap up here, this is what will happen. You connect this up to some way of measuring the current. Okay, so a galvanometer, something that can go. And what you'll find is, remember, as we're collapsing the flux, this will fight that. It'll build a field inside of it to counteract that, right? As we come around and we're building back up again, okay, now we're going from no flux to X is in our flux. It's going to spin current the other way. It's going to build up a field inside of it like this. So we can map that with time, and what we will get is something that looks like this. Okay, if we start at full flux to no flux, you get this. You get a sine wave, okay? You get a sine wave, and this represents max positive voltage to push in one direction, and this represents max negative voltage to push in the other direction. And we call this alternating or AC current as the voltage pushes charge back and forth. In North America, from your plug-in, you get 120 volts at 60 hertz out of your thing. And the last thing I'm just going to show you is the math. Okay, this is just the math on this, and then we're done. So what this represents is N, the number of coils inside that wire that you're spinning. You're not just going to spin one wire, you're going to spin a whole solenoid. Every loop of wire you add multiplies the amount of voltage you get, okay? This is your flux, which is the area times the magnetic field strength, and then T is the time for a flux change. So it is not the time for a complete turn, it's the time in this case for 1/4 turn. Okay, so 1/4 turn from full flux to no flux. Okay, and there you go. That's the last formula we need to know.